Hello developers, welcome to my video series on Microsoft Flight Simulator add-on workflow. Today we are going to learn about the PBR workflows, metallic roughness and specular glossiness or diffuse. I plan to have 3 episodes about the PBR workflow and PBR in general, one being on PBR technical aspects, which was the previous episode, PBR texturing workflow, which is this one, and then the Microsoft Flight Simulator materials. I hope you survived the previous physics lesson, and let's apply what we learned there to these PBR workflows. The ultimate goal of both workflows is to provide a set of textures that represent how the object looks in the real-world environment. To start out with color and grayscale maps of specific parts of the object that need texturing. You combine these maps into a group of textures that are used by the internal shaders, either in Substance Painter, Blender, or in the simulator that show how the object looks in real environments. The metallic roughness workflow uses the base color RGB map, a metallic grayscale map, and a roughness grayscale map. So we have a metallic one, a roughness, and a base color. The specular glossiness uses a diffuse base map, a glossiness grayscale, and a specular RGB map also. Both of these workflows also have common maps, ambient occlusion, normal maps, and height maps. The grayscale maps are represented by a single number, so a number from 1 to 0. The other maps, like base color, specular, diffuse maps, are RGB type maps, where the color is represented by 3 numbers for each channel, red, green, and blue. So the red channel goes from 1 to 0, green channel goes from 1 to 0, and the blue channel goes from 1 to 0. So what is PBR? Like we said before, physically based rendering, PBR. It's a method of shading and rendering that provides a more accurate representation of how light interacts with surfaces. It's referred to as a physically based rendering or physically based shading, PBS, and depending on what aspect of the pipeline is being discussed, PBS is usually specific to shading concepts and PBR is specific to rendering and lighting. However, both terms describe the process of representing assets from a physically accurate standpoint. So what are the benefits? Well, as an artist and developer, you can view the benefits of PBR from an artistic and production efficiency mindset. PBR removes the guesswork out of authoring surface attributes such as specularity, and since its methodology and algorithms are based on physically accurate formulas, it is therefore easier to create realistic looking assets. Assets will look accurate in all lighting conditions, and PBR provides a workflow for creating consistent artwork even between different artists. Metallic roughness workflow. The grayscale metallic and roughness maps. The metallic surface is represented by a value of 1. So if it's metallic, you represent that with a value of 1. A non-metallic, or what's called a dielectric surface, is a value of 0. Roughness on a surface is a value of 1, and non-roughness, or smooth, on a surface is a value of 0. So we have a metallic grayscale map, we have a grayscale map for roughness, and then we have an RGB map for the base color. Similarly, for the specular glossiness, the glossiness is the reverse of roughness. where the glossiness or smooth part is a value of 1, and the non-glossiness or rough is a value of 0. So specular glossiness is a little bit different with the reverse of the roughness component. There is also a base color diffuse RGB for both. 3 values represent the base color for each of the channels. And you combine these 3 maps in each workflow along with the common ones, the ambient occlusion, height, and normal maps, to generate the textures needed for the sim to show your aircraft in a realistic manner. This is a very high-level view of PBR, and if you want to know more, there's references in the Google with links and documentation about PBR that's in a lot more detail. If you recall from the previous episode about the physics of light and so forth, we had a dielectric F0 or Fresnel 0, which is an observer looking at an object at 0 degrees or straight on. The F0 for common dielectric materials is typically set to 0.04 linear or 4% reflective. In the metal roughness workflow, this value is hard-coded into the shader. Some metal roughness implementations, such as those found in the Substance toolset and Unreal Engine 4, have a specular control, which allows the artist to change the constant F0 value. Substance, this is output in a label called specular level. But we don't change the specular level in Blender because that basically adds an additional piece of information that the simulator won't understand. You may have seen the KHR specular as an extension, and it says it's ignored in the building. So you can't really change this. You have to just use whatever is in Blender. So it represents basically the 0.0 to 0.08 as shown in this diagram, and we saw this diagram in the previous episode. So basically 59 RGB, so the color is very, very low, 4% reflective for a dielectric. The base color, RGB, the base color map is an RGB map that can contain 2 types of data. Diffuse reflected color for dielectrics and reflectance values for metals. So what you've got in here is a base color RGB map. Depending on what you're looking at, if you're looking at a dielectric, then the numbers in the channels there represent the diffuse reflected color. And if you're looking at a metallic surface, that channel number refers to the reflectance values for the metal. So the base color map can be thought of as being somewhat flat tonally. That is, its contrast is lower than that of traditional diffuse maps. It is inadvisable to have values that are too bright or too dark. Objects tend to be much lighter in tone than we remember them being, and we can visualize this range in terms of the darkest substance being coal and the brightest being fresh white snow. Coal is dark, but it's not black or 0, and the color values we choose need to stay within the brightness range. As regards to brightness ranges, we are mostly referring to the dielectric reflected color. So you see the example where the dirt value has fallen below the correct brightness range. And the dark value should not go under 30 to 50 sRGB. So the base map looks like this, kind of flat, and you'll notice that the dark areas are not supposed to be too dark. this represents a good darkness for this material. And this is kind of an indication from the substance tools that green means good and red means not good. So if you have substance where it has an add-on that allows you to compare things, you'll see that if you get red here, that you have set up your base color incorrectly. Hopefully Substance Painter will stop you from doing that, but there is a possibility that you could set up the base color incorrectly. So colors are represented in the base color, albedo for non-metallic materials, and reflectance value for metals. The base colors should be devoid of any lighting information, with the exception of micro-occlusions. Dark values should be no lower than 30 sRGB or 50. Bright values should not be higher than 240. The reflectance for raw metal is going to be high in the range of 70 to 100% specular, which we can map to 180 to 255 sRGB. Metallic grayscale linear. Linear just kind of means there's no adjustment for gamma. The metallic map is used to define which areas of the material are denoted as raw metal or dielectric. A grayscale map, it operates in a manner similar to a mask, as it tells the shader how it should interpret the data that's found in the base color. So remember we said the base color has certain values based on if it sees metallic or if it sees non-metallic. The data in the metallic map does not contain real-world data, as it is directly used as a material value. It simply describes to the shader which areas of the base color should be interpreted as reflected color, in other words, a dielectric, and which areas denote a metal reflectance value. So the metallic map, the black and white metallic grayscale map, only makes the shader interpret what's in the base color map. And basically, in the metallic map, 0 black or 0 sRGB represents non-metallic, and 1 or white or 255 sRGB represents raw metal. In terms of defining raw metal and non-metallic, this metallic map is often binary, meaning one or the other, black or white, metal or non-metal. In practice, when the shader looks at the metal map, it sees white, then it checks for the corresponding area in the base color map to get the reflectance value for the metal part. Metal surfaces have two important aspects relating to texture. First, their reflectance value will be high in the range of 70 to 100% specular. Second, some metals can be corroded. We will look at these two aspects individually as we discuss with the creation guidelines. Metal areas that fall in this range will need to have a reflectance range of 70 to 100% reflective. Interpret as an RGB base color map, and will have information on reflectance and the reflectance color. Roughness, or grayscale linear. The roughness map describes the surface irregularities that cause light diffusion. As discussed in part 1, the reflected direction will vary randomly based on the surface roughness. This changes the light direction, but the light intensity overall remains constant. Rougher surfaces will have larger and dimmer looking highlights. A smoother surface will keep the specular reflections focused, which can appear to look brighter or more intense even though the same total amount of light is reflected. So in the diagrams here, we have a grayscale map of roughness. A value of 1 or a value of white means it's rough. So it looks as though what we have here is in the crevices, we have white. So white meaning rough. We don't have as much light being reflected directly. The darker areas here are much smoother. So black is non-rough or smooth. So this part here is represented here. So the much darker spot is the edge. So it's very smooth along this edge. So you get a lot of reflection, and it's not so smooth or in between. You might have some dirt or something. So it's neither smooth nor rough. So a smooth value of 0 or black, and a rough value is 1 or white. So this map looks black, represent the smooth surface, and white represents the rough surface. The roughness map is most creative map, and it allows the artist to visually define the character of the surface. It allows you to creatively tell a story about the condition of the surface. So you can see if it's corroded or has dirt on it, whatever. This is all handled through the roughness map. Roughness is a highly subjective area. You, the artist, are in full creative control. So a good place to start with a roughness map is on the normal map. You can see how bumpy it is with the normal map. You may want to add to it or remove roughness or make it smoother. Now, resolution and textile density. A byproduct of using the metal roughness workflow is that it can produce a white edge artifact, as shown here. The issue occurs also in the specular glossiness workflow, but in that case, instead of a white edge, you get a black edge on that. So these are similar. One is a metal roughness workflow, and the other here is a specular glossiness workflow. So with the metal roughness, the base color contains a brighter value for the metal reflectance, and this is interpolated with a non-metal diffuse color, which produces the white edge. With the specular glossiness, the diffuse map contains black since raw metal has no diffuse color, and the black value is interpolated with the non-metallic diffuse color, which in turn produces the black fringe. So the textile density has an impact on the white edge and also appear on the metal roughness workflow. To minimize the artifacts, make sure that their UVs provide adequate density to match the resolution. So good textile density is 1-to-1 kind of, rather than being a very small UV map compared to a large area. To summarize, for the metal roughness workflow, the pros and cons can be easier to author and less prone to errors caused by supplying incorrect dielectric F0 data, and uses less texture memory. Metallic and roughness are both grayscale maps, while the diffuse map is RGB, so it uses more memory. It seems to be more widely adopted workflow, so that's what we use in our Blender, and that's what we use in the ADOBE exporter. There is a metallic and roughness scale. There's a metallic roughness texture, so we're using the metallic roughness workflow in the simulator. You have no control over the F0 dielectrics. However, most implementations have a specular control to override this. I don't believe we have that ability. Maybe you do in Substance Painter, you can set it up, but you don't have any input to the specular value in Blender, or you shouldn't, because you should not be using the surface panel. You should only be using the Microsoft Material Parameters panel. If you do accidentally change some specular information, you'll get a KHR specular extension, and that will be ignored by the simulator. You'll kind of see it in the Blender rendering, but then you get a mismatch of how it looks in the sim. The edge artifacts are also more noticeable, especially at lower resolutions. We'll just go over the specular glossiness workflow just as a comparison to the roughness or the metallic roughness workflow. So here is the specular glossiness. We have a similar three main components or maps. We have the diffuse map, which is the same as the base color map in the metallic roughness. We have a glossiness, which is kind of opposite to the roughness. So glossiness is 1 and roughness is 0, while in the roughness map, roughness is 1 and smooth or glossiness is 0. Here we have the specular RGB, so this map here is an RGB map, while the metallic map is a grayscale map. This is the reason that you have less memory for the metallic workflow than you do for the specular glossiness. You have an extra larger texture here which uses 3 channels, while the metallic only uses 1, so less memory. The diffuse or RGB or sRGB map, as with the base color map with the metal roughness workflow, the diffuse map contains the albedo color. However, it doesn't contain any reflectance values, so there's no mapping of metallic, non-metallic here. There's just a diffuse map on the color. So raw metal would be indicated as 0, so you'd get a black spot with no color, while a dirt layer, let's say, would be some kind of color to be shown on the diffuse map. In the specular map defines the reflectance values for metal and the F0 for non-metal. The RGB map allows different values for dielectric materials to be authored. This is different from the metal roughness workflow where the dielectrics are hard-coded at 4% reflectivity. Can only be modified with specular levels. So the F0 for dielectrics will be a darker value. The metal reflectance can be colored, and some metals absorb light at different wavelengths. The F0 for both dielectrics and metals are authored by the RGB specular map, or this map. The specular map allows for different values of the dielectric F0 to be authored on the map. Since the specular map contains F0 for both metals and nonmetals, we'll break the map up into separate categories for each material type. So the example, we have rust or dirt, and we have different values for the base color, diffuse color, and the specular maps. For glossiness, it's a grayscale linear map, so there's only one number that is used from 0 to 1. So the glossiness map describes the surface irregularities that has caused light diffusion, similar to the roughness map. In this map, black means or represents a rough surface, and white represents a smooth surface. So it's the inverse of the roughness map in the metal roughness workflow. And what they've done here, is this document, I believe, is incorrect with the picture because it's basically a copy of the roughness diagram. Roughness is white when it shouldn't be. So this diagram is incorrect in my opinion. So it doesn't show you what it's really supposed to show you. Resolution and textile density, this is the similar issue as we had with the metallic roughness workflow, where you have a dark outline this time. And again, the best thing for you to do is to set your UVs properly. But since we're not worried about specular glossiness workflow, it's only an item for comparison. So pros and cons of specular glossiness. Edge artifacts are less apparent. You have control over the dielectric F0, but there are more cons. Because the specular map provides control over the dielectric, it's more susceptible to use of incorrect values. And it's possible to break the law of conservation of energy if you handle it incorrectly. It uses more texture memory, as we said, with the addition of an RGB map, and can be more confusing as it uses similar terminology to traditional workflows but requires different data. It also requires more knowledge of physically based guidelines such as the correct F0 for dielectrics, black for raw metals, diffuse color, and possible energy conservation if it's not handled in the shader. So there are other maps that are common to both workflows. One of them is the ambient occlusion map, or AO. In Blender, you'll see it as just O for occlusion. The ambient occlusion map defines how much of the ambient environment lighting is accessible to surface point. Things like the wheel wells of your aircraft, it's dark inside those. You'll have a dark area for ambient occlusion. Any creases or crevices and things like that, those will be dark. It's difficult for the ambient light to get at them. So some engines, such as Unreal Engine, have an option for screen space reflections. I don't think we have that. We don't have the ability to reflect the area around the object so that you can see reflections in it. In Substance PBR shaders, the ambient lighting is generated by an environment map, and it's multiplied by the AO, and the AO map is supplied by a texture sampler in the PBR shader. The AO should not be baked into texture maps, but only supplied as its own channel to the shader. So that's why we say the ambient occlusion shouldn't be put into the base maps. It's going to be a separate map that is exported from Substance Painter. So we just have examples here of ambient occlusion maps. Another map is the height map. So a height map is often used for displacement and rendering. So a height map will actually change the geometry based on whatever program you're using. We don't really have any height maps, so we're not changing the geometry of the actual object, but we will use the height maps to generate a normal map. So you get greater realism with a height map, or what's called bump mapping, and so forth. The next map is the normal map, and that's your famous bluey, green, purpley map that implies that there is some kind of surface irregularity on that, more than just the roughness. There's actual dents or creases or whatever, and a normal map is used to simulate those surface details. It's an RGB map, so where the components correspond to the XYZ coordinates of the surface normal. And it can be used to store the projected details of a high-resolution model to a low-resolution model. So you may make a perfect screw head, but what you want to do is you don't want to repeat that screw head in your geometry over and over 1,000 times. You'll take that high-res screw head and make a normal map out of it. It saves you polygons and allows for your object to be more performance friendly. So all of the normal maps and so forth. Substance Designer and Substance Painter use normal maps, and you can add them to your object. I've skipped over a lot of information in this part 2 of this document. If you feel you need some more information, but it's all related to using Substance Painter and so forth, try and read it by yourself if you want to. It's a lot of high detail stuff. I'm just trying to give you an overall gist of PBR painting or PBR workflows. And you can see here that one of our final looks is in the metal roughness workflow. Is the surface metal? If it's yes, the base color albedo represents the non-metallic material and is a reflectance value. The raw metal is black, as has no diffuse color. Diffuse color for the metal is not authored in this map and should be devoid of any lighting, the ambient occlusion. The base color reflectance part is the reflectance is authored in this base color. 70 to 100% specular, uses real world measured values, and you use oxidation and dirt layers. If it's not metal, then the base color is an albedo like it was before. The values represent a reflected color. The dark values should not go below 30 and no bright values above 240. And for a dielectric reflectance, it's 4% baked in and uses real world measurements. No values under 0.02 linear, and you can't find a value use 0.04. And similar for specular glossiness, there's a yes, no. If it's a surface metal, yes, your diffuse albedo map, or you have no, it's specular reference map. Just as a last item in this document, they have correct and incorrect comparisons in the metallic workflow. So your material will look something like this. Correctly, that means you have a base color map and a metallic map like this. Incorrectly, it'll look like this because you have a base color map like this, but you have a slightly different metallic map. And what they want to show you here is that with the dirt in this area here, you would have a corresponding area of black or non-metallic. I know it's a metallic surface, but if it has dirt on it, then it would be labeled here on your metallic map as non-metallic. While in this particular case, the incorrect value, you have the dirt. These two maps look basically the same, but it's labeled here in white, meaning that it's metallic. So metallic will turn out to be incorrect. Remember, red is bad. And in this particular case, we have an area here which is labeled as metallic. Again, some dirt that's labeled incorrectly. So just something to be aware of when you're using a metallic workflow. You may have a piece of metal, but it may be dirty, so it's considered non-metal at that point. Well, there you have it. A look at the PBR texture workflow. In our next episode, we'll see how this all ties into using Blender with the PBR Metallic Roughness Workflow, and we'll go through the material section in the SDK docs and explain some of the terms there. So you may want to read ahead. I know I had to read that section 10 times, picking up terms here and there, and it's much easier if you have an understanding of the PBR workflow. You know why they're using metallic, roughness, ORM, occlusion, roughness, metallic textures, and normal textures, and then detailed normal textures, and so forth. So good luck, and we'll see you next time.